All right, welcome everybody. Today we're going to talk about section 3.2, and we're going to introduce ourselves to a whole new different set of numbers called the complex numbers. It's possible that at this point you have only ever been asked to deal with real numbers, which are things that can be represented on the real number line. Today, we're going to extend our knowledge of the system of numbers to include imaginary numbers. If you put all the real numbers together with all the imaginary numbers, what you compose is something called the set of complex numbers. So, up until this point, you've never really been asked to deal with a non real solution. And if you have, you probably just said no solution. So, we're going to go ahead now and develop a whole new set of numbers, which we're going to use to identify any answers which don't have real solutions. So a couple of different diagrams here just to kind of set the scene a little bit. Notice that over on the right, if you're talking about the different sets of numbers, you're going to start with all the numbers, which technically all the numbers are called complex numbers. Then you can break complex numbers down into the real numbers, which is all you've really ever seen before, followed by the imaginary numbers, which is what we're going to talk about today. Then underneath the real numbers, notice that you have a bunch of different sets of numbers that you could be after that. So each of these number sets has an abbreviation, which I'm going to show you because this is a popular type of question on standardized tests. So please make sure you know that the complex numbers are usually denoted with the letter C. The real numbers are usually denoted with the letter R. Because rational numbers, you can't use R again. The rational numbers are actually called set Q. The irrational numbers are called set I. For integers, again, you can't use I again. So the integers are actually the Z set, followed by W for the whole numbers, and N for the natural numbers. So we're going to go ahead and talk a little bit more about the real numbers before we go ahead and bring in the imaginary numbers. So take a look at the diagram over here on the left. All the numbers inside this box you should have heard of before, but it's good to just have a little reminder. So notice that after classifying something as a real number, you can then classify it as being rational or irrational. So as a reminder, the rational numbers are any fraction, and it's also the repeating and terminating decimals. So the nice fractions and the nice decimals, things like 0.1 repeating, things like 0.25, things like 4/5. Any repeating or terminating decimal is called a rational number. Compared to an irrational number, notice you have the weird numbers like pi, square root of 2, square root of 3, anything that gives you a big, long, messy decimal. And this also includes any non-repeating decimal. So then after your irrational number, you can then get rid of all the fractions and decimals and be classified as an integer. That includes all the positives, all the negatives, and 0, which is basically all the tick marks on the number line. Once you get rid of all the negatives, that's where the whole numbers come in. And once you get rid of 0, those are called the natural numbers or sometimes the counting numbers. So again, before we even bring in the idea of imaginary numbers, it is actually pretty important that you understand all about the real numbers. So take a look here in example A. It says determine which sets of numbers, meaning there are going to be several, that each value belongs to. Simplify first as needed and assume that everything is in the set of complex numbers. So what that means is we're assuming that all of these values live in set C. So we're not going to write C every time because we assume that they're all going to automatically be there. So first, let's go through and simplify what we can. The square root of 9 is 3. The square root of 0 is 0. The negative square root of 4, the negative stays on the outside, and the square root of 4 is 2, so negative 2. The square root of 4/9, you can break that up into the square root of the numerator, which is the square root of 4, divided by the square root of the denominator, which would be 3. I can't simplify the square root of 2, and I don't know how to simplify the square root of a negative yet. So those are all my simplifies. And now again, look up here at the different sets of numbers. Assuming that they're all going to be in set C, you then want to decide how far down the list in terms of real numbers can you classify. So if you're talking about positive 3, 3 is a real number. It is also a rational number. It's an integer, it's a whole number, and it's a natural number. So the number 3 would belong to all of those sets. When it comes to the number 0, that's a real number. It's an integer. It's a whole number. Oh, sorry. So it's real. It's rational. It's an integer. And it's a whole number. It's not a natural number because the natural numbers don't include 0. So 0 would belong to all of those sets. Negative 2. Negative 2 is certainly real. It's definitely rational. It's an integer, and that's as far down the list as you can go. 2/3, definitely real, definitely rational, and that's it. Square root of 2 is absolutely real, but because it's a gross, messy decimal, it is irrational, and then obviously there's nowhere to go after being irrational. And then finally, on to the whole point of today's lesson. Millions of years ago, hundreds of thousands of years ago, however long ago it was, I'm actually not sure. People were working with, mathematicians were working with numbers, and at some point they got an answer to a question that was the square root of -1. They didn't know what to do with it, so they decided to make a whole new set of numbers where the square root of -1 is the imaginary unit, which we're going to simplify as to be the number I. So the square root of -1 is equal to I, and we're going to talk about that more right underneath. So the imaginary unit I, basically because not all quadratic equations have real solutions, they had to come up with a whole new set of numbers to represent non-real solutions. Two important facts that you want to know today. Today we're going to mostly focus on fact 1, and tomorrow we'll focus on fact 2. So the first is the definition of the imaginary unit, which is the fact that the square root of -1 is equal to the number I. Draw it as a lowercase I so as to not confuse it with the number set for the uppercase I. And then if you were to square both sides, if you square the square root of a -1, you get -1. If you square an I, you get an I squared, which gives us our second fact for today, which is the fact that I squared will always be equal to -1. So both of these statements are true. Both of these statements are very important in terms of complex numbers. You're going to use one or the other depending on the problem that's being asked. One other thing I want to point out, if you go back to this box over here on the right, there actually is no abbreviation for the set of imaginary numbers. They don't use a letter. They just call it the imaginary number set. So just FYI. Again, as a reminder, that uppercase I, remember, means the irrational numbers, which is why when you're talking about imaginaries, you have to use the lowercase. So the first thing you're going to be asked to do is you're going to be asked to find the square root of each value and simplify using imaginary numbers as needed. Just to point out, not every problem from this point forward is going to be imaginary. Every problem from this point forward just could potentially be imaginary. So take a look at number 1. Number 1, the square root of 81. That's a problem you've seen hundreds of times. The square root of 81, that's a perfect square, and that is just +9. That is it. Some of you might be thinking, well, is it plus or minus 9? The answer is no. That will come up tomorrow. In order for there to be a plus or minus, it has to be an equation, meaning there have to be equal signs and there have to be x squareds, neither of which exist in any of these problems. So for today, it's only one answer. You'll see tomorrow when it should be 2. So now take a look at number 2, the square root of -81. So what you're going to do for all of these problems is you're going to break down whatever is under the radical into whatever the biggest perfect square you can is, which in this case is 81, and then you're going to break it down into the square root of -1. The square root of 81 is still 9. By definition, the square root of -1 is I, which means the square root of -81 is 9i. So really, this is just using different notation. If you look at number 1 and 2, one has a real solution and one has an imaginary solution, but they both still have a 9. Take a look at number 3, the square root of 32. Because it's a positive, there aren't going to be any imaginaries. You're going to break the square root of 32 into the biggest perfect square, which is 16, and it goes in twice. The square root of 16 is 4. The square root of 2 is radical 2, which would simplify to be 4 radical 2. If you were to compare that to number 4, you would start the same way, square root of 16, followed by the square root of 2, followed by the square root of negative 1. Those three numbers would have to multiply underneath to be negative 32. Whenever you have all three parts in your answer, you're always going to put the whole number first, 4. Then you're going to put the I in the middle, and you're going to put the radical last. So the square root of negative 32 is 4i radical 2. And yes, it is important that you put the I in the middle when you have a whole number first and a radical part last. So then let's take a look at some harder versions of these. So 5 times the square root of 24. Again, no imaginary numbers are going to happen because there are no negatives. You're going to leave the 5. You're going to break the square root of 24 into the biggest perfect square, which is 4, times 6. Then the square root of 4 is 2. Now that the 5 and 2 are both on the outside, those are going to multiply. 5 times 2 is 10, radical 6. Again, not every answer from this point forward is going to have an imaginary. It just potentially could have an imaginary. For number 6, start with the 2 that's on the outside. The square root of negative 16 would be the square root of 16 and the square root of negative 1. The square root of 16 is 4. Now that the 2 and the 4 are both outside, it's a multiplier. The square root of negative 1, by definition, is an I. And 2 times 4i is 8i. You're going to multiply the real parts and then put the I in the back. In number 7, they're kind of trying to trick you because the negative is on the outside. If the negative is on the outside, you're not going to have an imaginary answer. You're going to have a negative answer. So make sure you know the difference. So the negative 4 is on the outside. The square root of 100 is just 10. Because everything pops out of the radical, you're going to multiply for an answer of negative 40. As hard as it could possibly get is something like number 8, where there's a negative on the outside and there's a negative on the inside. The negative on the outside means your answer is going to be negative. The negative on the inside means there's going to be an imaginary. So the biggest perfect square in 40 is 4, 10 times, square root of negative 1. The square root of 4 is 2. Negative 3 times 2 is going to give you a negative 6. The square root of negative 1 is I, and then finish up with a radical 10. If you're wondering, do you have to show all that work every single time? I mean, I guess not. Once you get good at these, it's possible you could be able to find the answer without doing that work, but it takes so little time that I actually think it's kind of worth it. And now we're going to go ahead and look at these powers of I and see if we can find anything that these powers have in common or any pattern that there might be. So starting with the fact, again, that the definition of I is equal to the square root of negative 1. That is never going to change. We've now seen it at least 3 or 4 times today, so make sure that you highlight it, circle it, know exactly where to find it. And then let's go ahead and see what happens as we take the powers of I and keep going. So by definition, I to the first is equal to negative 1. So if you were being asked to simplify I to the first, that would just be equal to I squared. If you go ahead and square both sides, you're going to get that I squared is equal to negative 1. I to the third, you could break I to the third up into I squared and I to the first because 2 plus 1 is 3. Because I squared is equal to negative 1 and I to the first is equal to I, you could actually say that I to the third is equal to negative I. And because I to the fourth can be broken up into I squared and I squared, both of which are negative 1s, you could say that I to the fourth is equal to 1. So those are the first four powers of I, and it turns out that those are the ones you need in order to figure out the pattern for the rest. So I to the first is I, squared is -1, cubed is -I, and I to the fourth is equal to 1. And of all that information, I to the fourth is the money step. So every time you break a problem down into an I to the fourth, you're really breaking it down into a +1, which means you can basically just get rid of it. So when I say I to the fifth, you're going to break I to the fifth down into I to the fourth times I to the first. Because I to the fourth is equal to 1, this is really 1 times I to the first, which is just I to the first. Because you can break I to the sixth into I to the fourth and I squared, I to the fourth is equal to 1, you're just left with I squared, which is equal to -1. I to the seventh can be broken up into I to the fourth times I to the third. I to the fourth is 1. I to the third is -I. And finally, I to the eighth can be I to the fourth and I to the fourth. Both of those are ones. 1 times 1 is 1. And notice that you get the same exact pattern for I to the 5, 6, 7, 8 that you did as I to the 1, 2, 3, 4. And it turns out that that is always the pattern. So the powers of I repeat in groups of 4. How do you take that information and simplify really, really, really big powers of I, without actually writing out all that different stuff? Well, again, it goes back to I to the fourth. I to the fourth is the money step. As many I to the fourths as you can possibly create, you're going to take that number out of your powers of I and then simplify whatever the remainder is. So take a look at the examples over here on the right. Simplify each using the powers of I. So your mission is to look for as many I to the fourths as you can, because every time you can take out an I to the fourth, you're basically taking out a 1. Here's another important piece of information. Anytime you have an I raised to something that is evenly divisible by 4, it automatically turns out to be a 1. So I to the 8th, I to the 12th, I to the 16th. Anything that is divisible by 4 automatically becomes a 1, which is exactly what happens here with I to the 12th. Because 12 is evenly divisible by 4, you know that your answer is going to turn out to be 1. If you want to see why, you could break this up into I4, I4, and I4, because 4 plus 4 plus 4 equals I to the 12th. Because each of those I to the fourths is equal to 1, you're getting 1 times 1 times 1, which is why that answer is just equal to 1. How do you kind of make a time saver? Well, what about I to the 22nd? You're going to take whatever the exponent is, 22. You're going to find a number close to 22, less than or equal to 22, that is divisible by 4. In this case, the closest one would be I to the 20th. As soon as you get a power of I that is evenly divisible by 4, that whole thing turns out to be a 1. You're then left with I squared, and I squared is always equal to -1. You have to know that I to the first is I, squared is -1, cubed is -I, and to the fourth is 1. So you would have to memorize those 4 facts, which again, because everything is open notes, you don't have to memorize. But if you know those 4 facts, that's why you're allowed to do these shortcuts. So I to the 31st, you're going to find a number close to 31, less than or equal to 31, that is divisible by 4, which would be 28. Anything to a number divisible by 4 just becomes a 1. You're just left with I to the third, which would give you -I. And finally, I to the 45th, very, very close to I to the 44th, with just a remainder of 1. Anything to a power divisible by 4 becomes a 1, which means you're just left with an I. So there's an example of each of the 4 things that you were left with. And just so you know, you can never have a power of I that is bigger than 1. So if you have a power of I that is bigger than 1, it means you're going to have to reduce it. All right, so then going back to just how complex numbers should look. So complex numbers always have to be written in what is called standard form of complex numbers. And a standard form of complex numbers is the following. You put the real part, which is the A, first. Then it's either plus or minus the imaginary part in the back. The imaginary part is always going to be represented by a B and then an I for an imaginary. And again, this is just a reminder of where the I comes from. Once you realize what an answer is supposed to look like, there's an idea that two complex numbers can only be equal if their real parts are equal and if their imaginary parts are equal. So look over here at example D. Find the values of x and y that satisfy the equation. So what they're saying to you in this problem is that you have a complex number on the left and you have a complex number on the right. The only possible way that those two complex numbers can be equal is if their real parts are equal and if their imaginary parts are equal. So you're going to set the real parts equal. You're going to set the imaginary parts equal, and then you're going to solve. So 2x equals 10, divide by 2, x must equal 5. If negative 7i equals yi, you can cancel out the i's, which means that y is negative 7. So it's almost kind of a silly question because it really is so easy. But again, what they're trying to tell you here is that you have two complex numbers. The only possible way that they can be equal is if their real parts are equal and if their imaginary parts are equal. So 5x equals 35. That can only be true is if x is equal to 7. Negative 20i equals yi. Cancel out the i's, which means that y has to be equal to negative 20. A few more things you have to do with i's for today, and the next of which is you have to be able to add and subtract complex numbers. In order to add or subtract complex numbers, you are only allowed to add the real parts together to get the real part of the answer. True for addition and true for subtraction. Then you have to combine the imaginary parts together to get the imaginary part of your answers. Again, true for addition and true for subtraction. So in this next set of answers, you're going to add or subtract. And again, you're always going to write the answer in which considered to be, oops, sorry about that. Just 1 second. There we go. Okay, so you're going to add or subtract, and you're going to write the answers in standard form. And again, in your homework or in your tests or quizzes, it's always going to say standard form. So that means A plus BI. So in number 1, even though there are parentheses, it doesn't matter. You are still adding them. So if you are being asked to add complex numbers, you're going to locate all the real parts, which is 2 plus 11. You're going to add those together and get the real part of your answer, which is 13. Then you're going to locate the imaginary parts. You're going to add them together, 9i plus negative 1i. 9 minus 1 is 8, but 8i. For number 2, this is a subtraction. So even though you're still combining the real parts with the imaginary parts, you have to do so via subtraction. So for the real part, you have to do 13 minus 8. 13 minus 8 gives you a real part of 5. Then you have to do 4i minus 4i, which gives you 0i. And when you have 5 plus 0i, you don't have to put the 0i. You can just go ahead and leave the 5. Just so you know, when you have A plus BI, that's called a complex number. If you have no i's, like this number, you're a real number. If you only have i's, then you're called a pure imaginary number. So just kind of a fun fact. Last but not least, number 3, so you're trying to add and subtract like terms. I'm going to go ahead and start by distributing the subtraction. So that's going to give me a 16 minus a 13 minus a 6i plus an 8i. You're going to combine only the real part first. 16 minus 3 is 13 16 minus 13 is 3. Then you're going to combine just the imaginary part, which is 3 plus 2i. A couple last minute things that you have to be able to do. So, a new vocab word, there is something called an additive inverse. An additive inverse is another complex number that if you add it to the complex number that already exists, everything should cancel out to be zero. When you see the word inverse, you should hopefully think of opposite. And because it's called the additive inverse, that means it's the opposite when you're doing addition. So notice for each of these three examples, I already give you some complex number z. What I'm asking you for when I ask you for the additive inverse is I'm asking you to find me a second complex number, y, such that when I add it to the original problem, everything should cancel out to be zero. Turns out that the question might sound hard, but it's actually very simple to do. What would you add to real 1 to get 0? Well, you would add negative 1. What would you add to a plus 1 imaginary to get 0? Well, turns out you would do a minus 1. So your answer is y equals negative 1 minus I. That is the additive inverse of z. Same thing in number 2. You're looking for a second complex number y, such that when I add it together, everything should cancel. Opposite of the real, opposite of the imaginary. And again, what you have found there is something called the additive inverse. Finally, take a minute, see if you can think about what the answer to number 3 would be. Again, you're trying to add these together to get everything to cancel out. And hopefully with very little thinking or work, you can go ahead and conclude that y must be equal to positive 2 minus 8i. So this is just kind of an introduction to complex numbers. There's much more to come with it in the next lesson and then for the rest of the year. The last thing I want to just talk about very briefly, you don't have to write this down, is maybe you're wondering, where would we ever see complex numbers? What are they ever used for? So if anyone out there is interested in any kind of engineering, you might know that electrical circuits have things called resistors, inductors, and capacitors. And so they all have, special numbers and special meanings. They're measured in something called an ohm, which looks like this fancy little letter here, which is called an omega. Turns out that complex numbers are a part of these electrical problems. Once you have, again, your three parts, your resistor, your inductor, and your capacitor, there is something called an impedance that you could be asked to find. And when it comes to the inductor and the capacitor, you actually do use imaginary numbers. You're using them to kind of create resistance and basically contribute to a reactance or a resistance. So it's actually kind of a silly problem. It's very easy to solve. We're not really going to spend too much time on it, but I really just wanted you to know that there is a real world application for imaginary numbers. The one that is used the most frequently is in electrical circuits. So if you ever come across one in your travels and you see imaginary numbers, now at least you'll be in the know. So